Welcome back to the Stay Ahead Cybersecurity Auditor Mastery series. I'm your host, and today we are tackling something every auditor eventually has to face head on: the network itself. In the next 20 minutes, go from reading the network as a black box to reading traffic flows, spotting weak segmentation, and asking sharper questions in the field. We'll move through the OSI and TCP or IP models and or IP addressing and subnetting, the core protocols carrying everyday traffic, the devices that enforce control, topologies, segmentation strategy, common attack patterns, and finish with a 10-point auditor checklist you can use on your very next engagement. Let's map the terrain. Every piece of data that crosses a network passes through seven conceptual layers. The OSI model, starting at the top, layer 7 application is where the user actually works: browsers, email clients, ERP screens. Layer 6 presentation handles encryption, compression, and encoding. This is where TLS cipher suits and certificate policy really live. Layer 5 session opens and tears down conversations, endpoints, governing session timeouts and token expiry. Layer 4 transport is where TCP and UDP operate along with port numbers, and it's almost always where firewall rules are actually written. Layer 3 network handles IP addressing and routing decisions. Layer 2 data link is where MAC addressing and switching happen within a local segment. VLANs and port security live here, and layer 1 physical is the literal cabling, radio signals, and voltages. Think physical port lockdown and a cabling closet access. As an auditor, this stack isn't academic trivia, it's a map. When someone tells you the firewall handles that, this model lets you ask at which layer exactly. A remembering trick many auditors use is the mnemonic: please do not throw sausage pizza away. One word per layer, bottom to top. In practice, the industry collapsed those seven OSI layers into a leaner four-layer TCP or IP model. Application covers OSI layers 7 through 5, HTTP, DNS, SMTP. Transport maps to OSI layer 4, TCP and UDP. Internet maps to OSI layer 3, IP and ICMP. And network access covers OSI layers 2 and 1, Internet and Wi-Fi. Here's the part that matters most for evidence review: encapsulation. As your data moves down the stack, each layer wraps it in one more header, like nesting envelopes inside envelopes. Raw application data gets a TCP header attached, forming a segment. That segment gets an IP header attached, forming a packet, and that packet gets an Ethernet header trailer attached, forming a frame. The only thing that actually travels across the wire. This is exactly why a packet capture shows layers within layers, and it's why a single control like TLS only protects certain headers, payload, and some transport metadata, while addressing information at lower layers remains visible to anyone watching the wire. Every IPv4 address splits into a network portion and a host portion, and the subnet mask or CIDR suffix tells you exactly where that split happens. Let's work an example auditors see constantly: 192.168.10.37 with a slash 26 mask. The slash 26 means 26 network bits and 6 host bits. 2 to the power of 6 gives 64 addresses in that subnet. Subtract 2 for the network and broadcast addresses, and you get 62 usable host addresses. Subnet boundaries for a slash 26 always land on 0, 64, 128, and 192 in the final octet. So 37 falls inside the 0 to 63 block. Why does this matter in field work? Undersized subnets force teams into temporary flat networks that never get fixed. A very common finding: Private address ranges 10.0.0/8, 172.60.0.0/12, and 192.168.0.0/16 should never directly route to the internet. If you see that in a routing table, flag it immediately. CIDR notation and firewall rules reveal scope at a glance. A /32 is exactly one host, while a /0 means literally everything. Overlapping subnets across different sites is a classic symptom of network growth that outpaced documentation. Core protocols and six protocols carry almost all everyday network traffic. So let's watch how they actually establish a conversation. TCP begins every connection with a three-way handshake. The client sends a SYN, the server responds with a SYN ACK, the client confirms with an ACK. Only after that handshake complete does real data start flowing. And this handshake is exactly what confirms delivery, ordering, and connection state for things like HTTP, email, and file transfer. UDP skips all of that for speed, no handshake, no guaranteed delivery, which is why it's the protocol of choice for DNS lookups, DOIP calls, and video streaming, where a little loss is better than a delay. Speaking of DNS, it resolves human readable names into IP addresses through recursive lookups. A poison DNS cache is one of the most damaging ways users end up on attacker controlled infrastructure. DHCP automatically assigns IP addresses, gateways, and DNS servers through a four-step exchange known as DORA: discover, offer, request, acknowledge. HTTP and HTTPS carry web traffic, with HTTPS wrapping the connection in TLS, but auditors should verify actual cipher strength and certificate validity, not just confirm a padlock icon exists. And ARP means maps IP addresses to MAC addresses on the local segment. Critically, with no built-in authentication, which is exactly why ARP spoofing remains such a persistent, low-effort attack. Every device on the network operates at a specific layer, and knowing which one tells you exactly what that device can and cannot enforce. A switch works at layer 2, forwarding frames by MAC address inside a LAN segment. A router works at layer 3, forwarding packets between different networks using routing tables. A firewall spans layer 3 through layer 7 depending on generation. Modern next generation firewalls can inspect all the way up to the application layer, not just ports and IP addresses. IDS and IPS systems also operate across that same range. An IDS detects known bad traffic patterns while an IPS actively blocks them in real time. A proxy operates at layer 7. Forward proxies protect clients by mediating their outbound requests. Proxy operates at layer 7. Forward proxies protect clients by mediating their outbound requests, while reverse proxies protect servers by mediating inbound requests. And a VPN gateway operates at layer 3, encrypting traffic between untrusted networks for both site to site links and remote access. Here's the audit angle. A firewall rule review means nothing if you haven't first confirmed which device actually sits in the real traffic path. Always ask for the current network diagram, then verify it against the live trace route, because diagrams drift from reality faster than most organizations realize. How devices are physically and logically wired shapes both performance and blast radius when something goes wrong. Star topology connects all nodes to one central switch. It's the standard for modern LANs, though that central switch becomes a single point of failure. Mesh topology builds multiple redundant paths between nodes, resilient but costly and typically reserved for core or backbone links. Bus topology relies on a single shared backbone, capable of legacy design you'll rarely encounter in a modern audit. And hybrid topology is what most real enterprises actually run. Star wired LANs joined together by a meshed wide area or core network. One practical tip from the field: topology diagrams age fast. The one you are handed hasn't shown a single change in the last 12 months. Treat that as a finding, if not as a fact you can rely on. Segmentation is the single biggest layer an organization has against lateral movement, and it turns one flat, high risk network into a series of contained zones. Picture it top to bottom. The internet sits at the top as fully untrusted. Just below it sits the DMZ, housing public facing web, email, and DNS servers, kept isolated from the internal LAN. Inside that, internal VLAN segment traffic by function, finance, HR, operation technology, guest Wi-Fi, each logically separated without needing new cabling. And at the core sits the crown jewel zone, ERP systems, PII data stores, programmable logic controllers, protected by the tightest controls and the smallest possible access list. VLAN separate broadcast domains logically. Properly built DMZ means a compromised web server never has a direct path into internal data. And zero trust flips the model entirely. It assumes breach, so every single request gets authenticated and authorized regardless of where it originates on the network. Here's a test you can run in the field. Pick any device in one VLAN and confirm concretely what it truly cannot reach. If nobody can answer that question with confidence, that's your finding. Segmentation. You don't need to reproduce an attack to audit around it. You need to recognize its fingerprints in logs and architecture. A man in the middle attack intercepts traffic between two parties. Watch for unexpected certificate warnings or duplicate MAC and IP pairings in your logs. ARP spoofing uses falsified ARP replies to redirect local traffic. The signature to watch for is one MAC address suddenly claiming many IP addresses. DNS poisoning corrupts a resolver's cache to redirect users to fake destinations. Look for DNSSEs being disabled or unexplained changes in resolution. Here, port scanning is reconnaissance. An attacker probing for open services visible as sequential connection attempts across many ports in a short window. Distributed denial of service attacks overwhelm a service with sheer traffic volume. Watch for sudden bandwidth spikes with no legitimate business driver behind them, and rogue devices, unauthorized access points, or switches plugged into the network show up as unmanaged MAC addresses or unexplained network access control exceptions. The auditor's job is in every one of these cases isn't to run the attack yourself, to confirm that detective and preventive controls exist, that they are properly tuned, and that they were actually tested in the last audit cycle, not just documented on paper. Let's bring this all together into 10 questions that separate a network diagram from a network you actually understand. The network diagram current dated within the last audit cycle. Are VLANs enforced by access control lists or only by naming convention? Does the DMZ have a documented tested isolation from internal VLANs? Default deny the baseline firewall posture with every exception logged. Are IDS and IPS signatures kept updated and are alerts actually triaged, not just generated? Is DNS traffic restricted to approved resolvers only? Are unused switch ports disabled or placed into a quarantine plan? Is remote access handled through VPN with multi-factor authentication, not open RTP or SSH exposed to the internet? Are subnet allocations documented and free of overlap across sites? And was the last network penetration test actually scoped to include segmentation testing, not just perimeter checks? Ask these 10 questions on your next engagement and you will surface gaps that a checklist only review would miss entirely. From the OSI stack all the way to zero trust zones, you have now got the map. Bring these questions into your next field work and you'll ask sharper questions than the diagram alone could ever answer. If this episode helped, subscribe for the next installment in the Stay Ahead Cybersecurity Auditor Mastery series and drop your questions in the comments below. This episode was brought to you by Audit.site AI powered compliance automation. See you in the next one.